Okay, great. So the next talk is going to be given by Máté Farkas from ICFO Barcelona, and he's going to tell us that Bell non-locality is not sufficient for the security of standard device-independent quantum key distribution protocols. So please, whenever you want.
Thank you. Thank you for the introduction, and thank you for reading out my title, because it's quite a mouthful. And I will present these concepts first in my talk, even though maybe some of you are familiar with Bell locality or quantum key distribution. I will have an overview of these, which will be the biggest part of the talk, and then I will quickly explain at the end our result, saying that Bell locality is not sufficient for this task in general. So this talk is about the work which we did in collaboration with ICFO in Barcelona and the University of Warsaw. So we used the full author list, and it's published in Swiss Letters and open access, so you can access it freely from here. I will start with describing the setup, which is basically the setup of Bell non-locality. And in this scenario, we consider two parties, usually referred to as Alice and Bob, which you can imagine that they are in some distant laboratories performing some sort of experiments. And the experiments are described by they can choose some different experiments. Usually we will think of these as some kind of measurements. So Alice is measuring a measurement labeled by X. She obtains a measurement outcome A, and Bob does something similar, and his input is labeled by Y, and the output is labeled by B. What we assume in these scenarios is that the events of these measurements are space-like separated, which also means that there's no communication between these two parties during the experiment. In this review paper, you can learn a lot about non-local scenarios. And the only thing that is available for us that describes this experiment is the so-called correlation, which is simply the probability of Alice obtaining the outcome A, Bob obtaining the outcome B, given that they've chosen the measurements X and Y. And we're interested in two physical models behind correlations. The first one is the kind of classical model, which is called the local hidden variable model, where the way we describe this experiment, the way we model the experiment, is that there is some sort of shared resource between the two labs, this lambda. We don't have directly access to it because we only have access to these outcome probabilities. So the model is that lambda takes some kind of value with a certain probability. This is this p lambda. And once this value of lambda is set, then what happens in these two labs is that there is a probabilistic function that takes the input and this shared resource and outputs, on Alice's side, outputs A with probability PA of A B max lambda, and on Bob's side, it outputs B given Y and lambda with some probability. But once we are conditioned on the settings and lambda, the probability of A is independent of the probability of B. So the only way A is correlated to B is via this shared variable lambda. And the set of correlations that can be written in this form forms a convex polytope, which we will call L, corresponding to local. And the extremal points of this polytope are the deterministic points, where the value of A is given as a deterministic function of the input, and the value of B is again given as a deterministic function fb of the input Y. The other model that you'll be interested in is the quantum model, where the shared resource is a quantum state, and the way the parties obtain outputs from the inputs and the quantum state is through quantum measurements. So we describe the measurements by some positive operator valued measures, and we write the outcome probabilities as using the Born rule on a tensor space. Again, the set of achievable correlation is a convex set. This is now not a polytope, and it's fairly easy to see that the local set is contained in the quantum set. Moreover, we know that this containment is strict, and this containment can be witnessed by so-called Bell inequalities. And the most famous one, arguably, is the Clauser-Hall-Shimony-Holt, or CHSH inequality, which is takes place in a scenario with 2 inputs and 2 outputs for both of the parties. And this inequality is an inequality on some linear combination of the probabilities. Okay, probably many of you know this. If you don't, it's not very important what the exact form is. What's important is that it's a linear combination of these kind of probabilities, and every local hidden variable model satisfies this inequality, that this linear combination cannot be more than 2. Whereas, using quantum theory, you can violate the CHSH inequality. And here I just give you like one quantum realization using the singlet state and certain eigenbases of some Pauli operators. You can actually get this value of the CHSH functional to 2√2, which is strictly larger than 2, which means that you can have some correlations in quantum theory that you cannot have in classical local hidden variable models. Which leaves us with essentially this picture of the set of correlations. We have the local set, which is a polytope. We have the quantum set, which is again a convex set, but not a polytope. And the local set is strictly contained in the quantum set. And this containment can be witnessed by Bell inequalities that every local correlation satisfies, but there are some quantum correlations that don't satisfy certain Bell inequalities. So this is kind of a schematic drawing of the sets, but this is actually also a specific slice of these sets of correlations in the scenario with 2 inputs and 2 outputs. So this is this is a very specific slice also for a given set. It's not just a drawing, but you can basically just think of it as a representation of these sets in general as well. So much for Bell nonlocality. I will now tell you briefly about device-independent key distribution, or DIQKD. First, the idea of key distribution is, again, having 2 parties. What they are trying to achieve is to establish a shared secret key. What does it mean? So Alice locally tries to establish, let's say, some bit string k of A, and Bob also locally wants to have this bit string k of B. Well, if we think of this as a shared key, they should be equal. And if you want the key to be secret, this means that it should be random for essentially any third party. So no one should be able to guess what the key is. This is the kind of very basic idea of key distribution. How do we use quantum theory to establish a key? You can, well, I give you just an example here. Let's say the way these parties establish the key is pre-sharing some states. I chose the singlet state again, and they are performing some measurements on this state. Now you can see if both Alice and Bob perform measurements in the computational basis on the singlet state, then the outcomes A and B will be perfectly anti-correlated. Whenever Alice obtains 0, Bob will obtain 1. Whenever Alice obtains 1, Bob will obtain 0. Now Bob can flip his bits, and in this case they end up with perfectly correlated bits. And it's also perfectly random, because if you look at the form of this state, it's impossible to tell in advance what the outcome of Alice and Bob will be, but they will always be perfectly correlated. So this is how you use quantum theory to establish a secret key. How do we go from here to device-independent key distribution? Is now we do not assume the exact form of the state and of the measurements. We possibly have various different measurement settings, and the only thing that we have access to is the correlation from this Bell scenario. And based on the correlation, we want to establish that it is possible for Alice and Bob, using some public communication that might be listened to by any sort of eavesdropper, that they establish a secret key eventually. So to give you a bit more idea how to do this using the Chsh inequality, which was in this paper. So remember in the Chsh inequality, we had 2 inputs and 2 outputs for each party. Now I add a third input for Bob, labeled by 2, and I choose this to be the same measurement as the 0 setting for Alice. And what we also know, well, one way to think about it is that if I see the maximal violation of the Chsh inequality, this essentially certifies my setup. This is something called self-testing. So if Alice and Bob observe their correlations maximally violating the Chsh inequality, they know exactly what the state is. Well, not exactly, but basically up to some like trivial mappings. They know what the state is and the measurements, and they basically know that the outcomes of these 2 settings are perfectly random and perfectly correlated. So sometimes just from the correlations, you can actually say, well, about your setup, and you can deduce that it is these correlations are useful. You can extract the secure key from them. So this is an example, but now I move on to the generic scheme of these standard QKD protocols. So in the first step, Alice and Bob measure their state. There are n copies of the state, let's say, and they measure them in these measurement rounds, and they collect the outcomes. So they have like n bits and bits of outcomes, and we will be interested in the case when the number of rounds goes to infinity. Now, after they are done with this data collection, they need to reveal some part of the data, which means that Alice will announce some part of his inputs and corresponding outputs to Bob and Bob to Alice, so that they are able to estimate the correlations actually, because otherwise they only have access to the marginal correlations, which is not enough. So this is a necessary step to estimate the correlations, and then this part of the data is discarded because these are announced in the public channel. The next step is what we call standard in the standard QKD protocols, because most of the known protocols and the ones that are proven to be secure use this step in which the outcome for the rest of the data, which was not discarded in the estimation round, the inputs are announced. So Alice tells Bob which inputs she chose in each round, and Bob tells Alice which inputs he chose in each round. In the CHSA protocol, you can think of it as like the parties want to know when they chose the settings that are actually perfectly correlated, because the other settings are not correlated. So they announce this these settings publicly, and after this, they are still allowed to exchange arbitrarily many messages in both directions. And using these messages and all the information, they locally try to establish the key KK and KP. And the figure of merit that we use in QKD protocols is the key rate, which is the mutual information of these 2 random variables that represent the key. We normalize it with the measurement rounds and take the asymptotic limit. And the key rate R is defined such that this normalized mutual information is larger than R and some epsilon for all positive epsilon. And also the mutual information of all the messages and E. So this is the information of a potential eavesdropper. In the next slides, I will put like a specific model behind the eavesdropper. So if you have some eavesdropper, the knowledge of the eavesdropper and these messages that have been publicly exchanged with the key, the mutual information of the eavesdropper basically with the key should be smaller than epsilon for all positive epsilon. So now I put a specific model behind the eavesdropper, which is called an individual attack, in which case we assume that since Alice and Bob don't have access to, they don't know what the exact form of the state and the measurements are, we basically give these to the eavesdropper. So the eavesdropper is essentially distributing the states. So in each round, the state might be different, and in fact, the state that Alice and Bob see is just the average of these states. And also the eavesdropper might have manufactured the devices that Alice and Bob use, so the eavesdropper know what the measurements are. Initially, she doesn't know what the settings are, and hopefully never knows what the outcomes are. That's the kind of aim in QKD. So eventually, Alice and Bob will announce their input, and at this point, the information of the eavesdropper is, well, she knows in each round which state they were measuring, this row J. She knows the measurement, the form of the measurement, and now also knows which measurements have been chosen in this round. So in each measurement round, using this information, the eavesdropper can make a guess on essentially the joint outcome of Alice and Bob. And this will be denoted by E. And okay, for a specific protocol, I might have a specific strategy of how the eavesdropper will get this information E. And I can write down a tripartite distribution P of A, B, and E for every setting there. And this will be so this is our classical distribution, and I can use this now to estimate the key that Alice and Bob can extract from their outcomes. And to extract this key, they're still allowed to exchange two-way messages. So kind of the big picture again is the parties start with the kind of quantum part. They collect data and estimate the correlations, and we're kind of now interested in the question which correlations can be useful for the QKD. The next step is we assume these standard protocols in which the inputs are announced, and using a specific eavesdropping model, we can build these tripartite classical distributions, after which we can use results from classical key distribution. Namely, what we will be interested in now is deriving upper bound on the key rate. So starting from a correlation, we build, given a specific eavesdropping attack, we build a tripartite classical distribution, and from this we can compute this, what is called the intrinsic information, which is essentially the conditional mutual information of Alice and Bob given the eavesdropper's information. And there's also an optimization over stochastic maps of the eavesdropper. This has been shown to be an upper bound on the key rate in the classical scenario. So actually, we're interested in the question, what bipartite correlations are useful for QKD via computing upper bounds on the key rate with a specific eavesdropping attack. And before we go to the specific attack, let's just see that Bell nonlocality is necessary for the security of QKD, because if you have a correlation that is local, it can be written as a convex combination of deterministic correlations, and giving this local hidden variable to the eavesdropper basically knows in each round exactly what the output of Alice and Bob are. So Bell nonlocality of the observed correlations is necessary for the security of the key. And what we show in this work is that it is not sufficient for these standard protocols. The way we show this is that we come up with a specific eavesdropping attack, fairly simple individual attack, and apply this to a large family of non-local correlations. And then we compute the upper bound of the key rate. Then whenever you see that the upper bound is 0, you conclude that this correlation is not useful for accepting a secure key. The eavesdropping attack is what we call the convex combination attack. And for a given observed bipartite correlation, we write it as a convex combination of some local correlation and some non-local correlation. Every correlation can be written in this form. And we call the local fraction QL, and the non-local will be 1 minus QL. You can think of it as the eavesdropper distributing to the local state with probability QL, and the non-local state with probability 1 minus QL. And after this, the tripartite distribution can be written again as a convex combination of the local part times, in this case, Eve knows exactly the output of Alice and Bob, so Eve's variable equals Alice's and Bob's variable. And in the non-local case, what we assume is that if the eavesdropper doesn't know anything, we denote this by this question mark. She could have some kind of knowledge, but it's not necessary for us. So for a given observed correlation, if we choose a specific non-local correlation to write this this convex combination. If you want to maximize the local fraction, this QL, which is kind of the most pessimistic case, because in the local rounds, the eavesdropper has maximal knowledge. So if you maximize this QL for a given observed correlation and the given chosen non-local correlation, this is a linear program. This is efficiently computable, and this gives us the full tripartite correlation, from which then we can compute upper bound on the key rate, which is just the average of the intrinsic information for a given setting pair X and Y, and then we can even choose weights for choosing the settings X and Y. So starting from a bipartite correlation, we can, using this convex combination attack, we can compute upper bounds on the key rate. The correlations that we apply this convex combination attack to are correlations that can be written as measuring the Werner state, which is the convex combination of the singlet state with the maximally mixed 2-qubit state. There is this one parameter called the visibility, which is the fraction of the singlet state. So we're interested in correlations that can be written as measuring the Werner state with some projected measurements, even arbitrarily many. We don't restrict the number of measurements here, even infinitely many. And we don't require the correlation to actually arise as measuring the Werner state with projected measurements, just that it can be written in this form. But we only assume that the form of the correlation. And why we chose this state is that it is known that for this state, there is this visibility, this parameter VL, up to which point, no matter what projective measurements I choose here, the correlations I get will be local. This is in this first paper, and in the second paper, it's been shown that there is this VNL visibility, at which I can already find projective measurements that give rise to a non-local correlation. This will be, we will use these visibilities in the convex combination attack and in our conclusions. So if you apply the convex combination attack to these kind of correlations, the way we apply it is basically, it's fairly easy now because I can just choose the local state to be the local visibility, the Werner state with the local visibility. So this guarantees that whatever the measurements are, the correlation will always be local. And I choose the non-local state to be just the perfect singlet state. And this gives rise to the convex combination attack for arbitrary correlations that use the Werner state. And I can now actually compute analytically this local fraction. It only depends on the visibility of the original Werner state. And given the local fraction, I can then compute the tripartite distribution. I can compute the upper bound of the key rate using the intrinsic information. And what we find is that up to this value, this B critical, the upper bound is 0. Therefore, Alice and Bob cannot extract a secure key from these correlations. And what's interesting is that actually this critical visibility is larger than this non-local visibility, which means that in this region between these two, there are non-local correlations that cannot be used for standard QKD. And this is essentially the main message, that there are these correlations, and it's a large family of correlations, because if you choose a Werner state with visibility in this region and arbitrary projective measurements, this will, well, many of these will give rise to non-local correlations, but you cannot use these to extract a secure key using standard QKD. The implications and the limitations of this result. Well, first, all the commonly used protocols are insecure even though the correlations are non-local. So if you think of the CHSH-based protocol, this is the first graph in terms of the visibility, but you can also think of this as in terms of the Bell violation, basically. In the perfect case, Alice and Bob can extract 1 bit of key. Then this shaded gray area is the lower bound on the key rate. So it's been proven that up to sort of this point, Alice and Bob can extract a key. Then there is the straight dashed pink line, which is an upper bound recently derived using intrinsic non-locality, and this dashed curve is again a recent upper bound using quantum intrinsic information. And the solid green line is our upper bound, which goes to 0 at this critical visibility, even though in this region the observed correlation is still non-local. And then you can also put this result in the set of correlations. So as I told you before, this is actually a specific slice of the set of quantum correlations, and we can show that there's this region outside the local set which is non-local, but you cannot use these correlations to extract the T using standard D and QKD. And about the limitations, what we couldn't show is that in protocols in which only one of the parties announced their settings, we couldn't get a 0 upper bound. So there are like fairly few protocols, relatively old ones, that propose these kind of scenarios. In the perfect visibility case, these usually give lower key rates, but it might be the case that in the large noise regime, these kind of protocols are actually advantageous because they might be more robust to noise if they don't know at the minute. And that's all I wanted to say. Thank you for your attention.
Thank you very much for the very interesting talk. And now it's time for a few questions. So please, if you have any questions, just write them in the chat or in a Slack, as you wish. In the meantime, as we get some other questions from some other participants, I would like to ask you something. So from this work that you've been presenting right now, what are the next lines to continue on? Like, as you were working at the end in these limitations of the model, are you thinking on some possibilities to overcome these limitations? And can you explain a bit on them, please?
Yes, so this would be like one of the natural things to do. Basically, to adapt this Convex combination attack to these kind of protocols when only one party announces the setting. Yes, it is not exactly clear at the minute how to do that, but there might be a lot of room for improvement because the attack that we use is a very simple attack. It's a simple individual attack. So we could go to coherent or collective attacks, which might increase, might decrease the upper bound. We probably need to use measures other than intrinsic information because, yes, basically as you can see from this paper, this is a paper of Kołodyński and Antonio. The intrinsic information upper bounds, in this case, when you don't take into account that the parties announce their settings, it's fairly unlikely that it will lead to a 0 upper bound. So we might also need to look for different upper bounds for this, different kind of different measures of upper bounds, like information to different than the intrinsic information.
Okay, I see. Thank you very much. And if there are some further questions, please I'll refer them to Slack so that you can continue the discussion there. So thanks again for the very interesting talk.